Hi science friends, today we are talking about colligative properties. So this lesson's just a little bit longer today, so I apologize. If you don't want to write everything down, I can give you a printed copy of the notes when we come back to class on Wednesday and Thursday, so don't worry too much about trying to get everything down if you just want to pay attention more to what I'm talking about. So today we're talking about colligative properties, and so when we have a solution, like a pure water, for example, we know that water is like the universal solvent. That was one of our properties of water that we talked about because it's a polar molecule and it tends to attract other molecules and things dissolve well in it. But when things dissolve in it, it changes it. So the properties that water once had, like its boiling point, for example, and its freezing point, and its vapor pressure, those are the three colligative properties that we're going to talk about today. When you add salt to water, the freezing point is not the same as it was anymore. The boiling point is not the same as it was anymore. And so these properties are called colligative properties. They change depending on the number of particles dissolved in a given mass of a solvent. So the freezing point for just adding a little bit of salt is going to be different than it would be if you add more salt in the same amount of solution. And so there's ways to calculate that, and that's what we're going to be working toward in the next couple of lessons. So as I mentioned, the three colligative properties that we are going to learn about, the first is vapor pressure lowering. So when you add a solute to a solvent, be it water or something else, it is going to lower the vapor pressure, okay? Now, let's review what is the vapor pressure. Vapor pressure is the pressure exerted in a liquid, over a liquid in a closed system. And so here is our liquid, here's our pure solvent on the left. The vapor pressure is the pressure that exists right here. In a closed system, so you see this jar has a cap on it. So if you have the cap off, then the vapor pressure is going to be equivalent to the atmospheric pressure. And so there's not really a vapor pressure, so to speak. But when you have a pure solvent, it's going to have a higher vapor pressure. When you add a solute to that mix, there is going to be a lower vapor pressure, okay? So in the first picture, the liquid and the vapor above it are in equilibrium. But when we add that solute in the second picture, that equilibrium is disrupted. These water molecules instead, the solvent here, are going to want to pair up with the solute. They try to combine and form to them. Like we saw in those diagrams back when we talked about water is such a good solvent, they try to surround those solute particles and they bond with intermolecular forces. And so that reduces the number of free particles that are up here that cause the vapor pressure. And so, as a result, the vapor pressure is lowered because these particles have essentially gone back into solution to bind with the solute, okay? And so that's the effect that vapor pressure. Solutions containing a solute that is non-volatile, so that means it's not easily evaporated. Something that evaporates easily is volatile. So if we're talking about a solute like salt, salt doesn't really evaporate very easily. It's going to have a lower vapor pressure than the pure solvent, okay? The next colligative property that we're going to talk about is boiling point elevation. So adding a solute to a liquid solvent is going to decrease the vapor pressure, as we just said, which in turn raises, hence the term elevation, the boiling point, okay? So if you remember, this is kind of key, this part in parentheses. The boiling point is defined as the amount of energy required for the vapor pressure to be equal to the atmospheric pressure. So if we lower the vapor pressure, then that's going to cause the boiling point to be raised, okay? And so boiling point elevation is another thing that we see. So if we add a solute, then it's going to raise the boiling point because it takes more to make that equal to the atmospheric pressure, okay? So that's boiling point elevation. The last colligative property is freezing point depression, okay? And so the freezing point is going to drop. And so now all of these colligative properties, remember as I mentioned previously, are proportional to the number of solute particles in solution. I had that up here at this beginning slide. Depend on the number of solute particles in solution, okay? So if you add more solute particles, it's going to change the difference more drastically. If you add more salt to water, it's going to make the boiling point be higher, okay? Now, we use these phenomenon a lot. We use boiling point elevation when we cook. If you're boiling noodles on the stove, the chef's frequently going to add salt to a pot of boiling water because it raises the temperature that water boils at. And so instead of boiling at 212 Fahrenheit or 100 Celsius, it's going to boil just a little bit above that. And so that means your noodles are going to cook hotter and they're going to cook a little bit faster and better, okay? We use this freezing point depression or freezing point lowering when we're salting our roads. When we put salt on the roads, that drops the freezing point down lower. And so as a result, water's not going to freeze at 32 degrees Celsius. It's going to freeze a little bit lower, and it's going to help to melt some of that ice. Okay? And so while you don't know what these things are, we use the science behind these things every single day. Okay? Now, one thing that I want to point out about this red part that I've highlighted here is that we have to talk about ionization constant. So if we're talking about glucose is C6H12O6. It's a covalent molecule. So when you put glucose in water, you keep these big glucose molecules. It's drawn as a hexagon because each point of the hexagon represents one of the 6 carbons, okay? And so it doesn't break apart into carbon and hydrogen and oxygen. Covalent compounds don't do that. They stay intact, okay? Now, ionic compounds do that. Here we have sodium chloride, so that's NaCl. And so you see it's broken down into equivalent green and yellow parts, right? And so this one has an ionization constant of 1 because for every glucose, there's just 1 part in the water. This one here has an ionization constant of 2, okay? Because for every salt, there's 2 parts. There's the Na and there's the Cl, okay? Now look over here at calcium chloride. Calcium chloride is CaCl2. We know that because calcium has a positive 2 charge, chlorine has a negative 1 charge. So to write that correctly, we have to have 2 chlorines to balance that calcium. So we can't forget how to name and write these compounds. So calcium chloride is CaCl2. So it has an ionization constant of 3. And so what you see here is you have, for every calcium chloride, you have a Ca and 2 Cls. And so your Cas here are purple, so you see 3 of them. And then you see those 2 that maybe go with that one. You see these 2 that, were bonded with that one. And those 2 that were bonded there. You see twice as many chlorines because of the way that formula and that compound is made. Okay? So what this means is if you put equivalent amounts of glucose, sodium chloride, and calcium chloride in a solution, that the calcium chloride is going to have 3 times the effect of glucose. The sodium chloride is going to have 2 times the effect of glucose, okay? So let me give you an example. Sorry, that flipped on you. If you add 1 mole of glucose to 1,000 grams or 1,000 milliliters of water, then the water will freeze at negative 1.86 degrees Celsius. That's the freezing point of water. So it dropped it down from 0 degrees Celsius to negative 1.8 degrees Celsius if you add 1 mole of glucose, okay? If you add 1 mole of sodium chloride, okay, it's still the same number of particles, because remember, that's what a mole is. It's 6.022 times 10 to the 23rd particles, okay? But it's going to break up into the different pieces. So now it's really twice as many pieces. And so it's not going to be negative 1 point. This one that we said was negative 1.86 degrees Celsius, okay? This one is negative 1.86 degrees Celsius times 2. So it's really negative 3.72 degrees Celsius is the temperature that it's going to break down at. This one is going to be negative 1.86 degrees Celsius times 3 because it has an ionization constant of 3, okay? So that's really important. And the same thing applies for boiling point elevation, that the bigger the ionization constant is, the higher up it's going to elevate the boiling point, okay? So I hope that makes sense to everybody. I know that's kind of a lot, okay? So the magnitude of the freezing point depression is proportional to the number of solute particles dissolved in the solvent and doesn't depend on its identity. It doesn't matter. It's not because it's glucose or it's not because it's salt. It's because of how those break down in the solution, okay? So if you had sodium iodide, it's going to have the same effect as sodium chloride because it still breaks down into 2 parts, okay? If you had calcium bromide or, anything that breaks down in 3 parts, it's going to have the same effect, okay? Because it's just the number of solute particles that affects its identity, all right? And notice the change isn't huge, negative 1.86 degrees Celsius, but it's enough to make a difference, okay? And then again, if you added more moles or a smaller volume of water, then it's going to change that as well, all right? So let's do just a little bit of math. Because we're going to need this as we go into the rest of our calculations. So colligative properties depend on the solute concentration, as we just mentioned, the number of particles in the solution. And so we can express these as 2 different ways. The first way is a measure called molality, all right? Molality is not the same thing as molarity, okay? Remember, molarity is the grams of solute per liter of solvent, okay? Molality is the moles of solute per kilogram of solvent, okay? So these are different. These are not the same. Molarity is capital M. Molality is lowercase m, all right? When you abbreviate molality, you write it as molal, M-O-L-A-L. So that's different than mole, like a quantity, M-O-L, all right? So be sure you're writing these correctly as you're answering your questions and you're doing your assignments, all right? So to prepare a solution that is 1 molal, we would add 1 mole of solute. So let's say a salt solution, a 1 molal salt solution. We would add 1 mole of solute of salt, which in sodium chloride, I don't know. You'd have to figure out how many grams that is. This molar mass, I don't have a periodic table in front of me, but the molar mass of sodium plus the molar mass of chlorine. Add those up, how many grams it is. I want to think it's 58 maybe. Grams in 1 kilogram of water, okay? Moles of solute per kilogram of solvent, all right? So that is how you calculate molality. The other way that you can express colligative properties is in what's called a mole fraction. Now, a mole fraction is just a ratio. And this down here looks really complicated, but I promise it's not as bad as it looks. So a mole fraction is the ratio of moles of solute to the total number of moles of solute plus solvent, or the total number of moles of solution. So if we look at this X's and A's and N's and all this stuff at the bottom, if we have Na moles of solute A and Nb moles of solvent B, the mole fraction Xa is equal to the number of moles of solute A, which was this, over the number of moles of solute A plus the number of moles of solvent B. Okay? X and N are just variables. They're just, plug any number in. Okay? Same thing over here. If we've got our solvent B over the number of moles of solute plus solvent. Okay? So essentially here we have solvent over solution. Moles of solvent over moles of solution. Here we have moles of solute versus moles of solution. Okay, and it's just a fraction, it's just a ratio. So we have a couple of calculations to do with these. So let's take a look at these first two together. How many grams of potassium iodide must be dissolved in 500 grams of water in order to produce a 0.060 mole Ki solution? Okay, so we have 500 grams of water. Okay, and so in our Ki solution, that is going to be, if it's a 0.060, what that means is we have 0.060 moles of Ki per 1,000 grams. Over here I think I said a kilogram, but remember 1 kilogram is equal to 1,000 grams. So I just used 1,000 grams since this was already in grams. I could have changed that to 0.5 kilograms. Either way would have been just fine. Okay. Of water is going to be our solvent. Okay. And then times, we're going to have to know the molar mass. So 1 mole of Ki, we need that on the bottom so we can cross out. I've already been able to cross out these. Is how many grams? Well, I have to add that up on my periodic table. And so I think if you add up Ki, the molar mass is 166 grams of Ki. Okay? So if you put this in your calculator, 500 times 0.060 times 166, and then divide that by 1,000, you should get 5.0 grams of Ki as your answer. All right. Let's take a look at the next one. It says compute the mole fraction of each component in a solution of 1.25 moles of ethylene glycol and 4 moles of water. Okay, so let's do our ethylene glycol first. So the ethylene glycol is 1.25 moles over our total, which is 1.25 plus 4.0. Okay, and those should both be moles as well. So if we do that, 1.25 over 5.25, you should get 0.0238. Okay, now there's no units on this because it's just a fraction or a ratio. There's no units here. Okay, so let's do the next part, which is our water. So we have the water part on top this time. So it's 4.0 moles over the total, 1.25 mole plus 4 mole. Okay, so again, that's going to be 4 over 0.25, and this one turns out to be 0.762. And so that is the mole fraction for each, for the ethylene glycol, and the water. Okay, now what you should notice about these two is that they equal 1. Your mole fractions always have to total up to 1. If they don't total up 1, you've done something wrong. Okay? All right, so here are 2 for you to try, 1 mole fraction and 1 molality calculation. Pause me for now and then come back and check and see if you got them right. All right, so if you've worked these, you should have gotten 12.6 grams of sodium fluoride for the first one. For the second one, for the mole fraction of ethanol, it should have been 0.375, and then the mole fraction for water should have been 0.625. So let's take a look at them. The first one, you start with those grams of water, so 750 grams of water, and then we're going to multiply by the molality of sodium fluoride. So remember, molality is if it's 0.400 mole, then that means it's 0.4 moles per 1,000 grams or 1 kilogram of water. Okay, and so that's what I've done there. Remember, we're doing dimensional analysis yet again here, and so keep track of what you're doing. By crossing out. We crossed out the grams of water. We crossed out the moles of sodium fluoride. So then that last step there was to multiply by the molar mass of sodium fluoride, which I calculated to be 42 grams. And so when you multiplied that across 750 times 0.4 times 42, and then to divide it by 1,000, I got 12.6 grams of sodium fluoride. Now on the second one, ethanol, they gave us 300 grams over a total 800 grams for the 300 grams of ethanol plus the 500 grams of water. And so that fraction was 0.375. And then for the water, it was 500 grams over that total 800 grams again. And so that gave you 0.625 for the mole fraction for water. So I feel like both of those were pretty easy. You'll have a worksheet to practice some today. If you have any questions, let me know. And if not, then you'll have a great day.